Hey, sorry about getting cut off there. The time constraints on the Screencastify is a little limiting with 5-minute videos. So this one I should be able to go a little bit faster without the initial explanation. So I was saying before at the end of the last video, these answers at the bottom of your synthetic division row, these represent the polynomial that remains for your quotient with the terms that are always 1 degree less than the term you start. So since this is the second degree polynomial that we started with, and when we're dividing out a first degree, your first term here is going to be left a first degree. So this is going to represent like your x column, and this one is going to represent like your constant column, okay? So in other words, what this answer means is that the quotient turns out to be 3x minus 28 plus a remainder of 130 divided by the factor always. So this is going to be x plus 5. So in other words, x plus 5 goes into 3x squared minus 13x minus 10. It goes in 3x minus 28 times. However, there's a remainder of 130. What this is also useful for helping us out with is evaluating functions. So you see how we plugged in a negative 5 as the x root value for that factor? That's kind of like me saying what the remainder theorem says, whatever factor you divide by, that number, right, is the same as me plugging in that input into the function and evaluating it. So when I plug negative 5 into the function 3x squared minus 13x minus 10, I get an answer of 130. That's what this means in terms of that function right there. So if I were to plug negative 5 in, I would get 130. That's what the remainder theorem says. Whatever factor you're dividing by, that root value from that factor, if you were to plug it in as an input, the answer is the same as the remainder. Okay, so now kind of using synthetic division, which is the important process to kind of gather from here, notice there's one thing different about this example, and it's very key for some of the traps for synthetic division. When you're setting up your coefficients, every power term, which is why we studied power functions earlier, has to be represented in the polynomial from highest down to lowest. So here you have a second degree, here you have a first degree, here you have a 0 degree, which is the constant. Every power term is represented. Here you have a second degree, you have no first degree term, but you've got a constant or 0 degree. So technically what you have to write in here is that there's a 0 coefficient for the x term. That power term has to be represented. So if you don't include that 0 as like kind of a placeholder, it's going to throw off your values when you do synthetic division. So here you have a coefficient of 1. Here you have a coefficient of 0. And then here you have a coefficient of negative 4. And now we can set up, this is going to be the remainder spot. Here's going to be the value of the root that we're going to plug in based on the factor. So I'm going to use a negative 4 as my x value from that factor. Now I've got my synthetic division board set up. I can use the same process that I was doing before. So if we add straight down, we get 1. And then if we multiply diagonally, right, that goes this way, we get negative 4. And then again, if we add straight down, so we add straight down here, we get negative 4. And if we multiply diagonally, negative 4 times negative 4 is positive 16. And then again, if we add straight down, this is going to add up to positive 12. So what this says again is that if I were to take my function, the original one, x squared minus 4, and divide it by x plus 4, I get 1x minus 4 with a remainder of 12. So this answer says x minus 4 with a remainder of 12. And I'm dividing by x plus 4 as the factor. So that would be your quotient. But in other words, what this means, I can also write, if I were to take this, let's call this function g of x squared minus 4. If I were to take g and plug in a negative 4, I would get a remainder of 12, which the output would be 12. That's kind of what that remainder theorem is saying up above. Okay? Now, using this, we can actually come up with a fast way to plug in values using this concept of remainder theorem. So if I were to take an example like this would be kind of tough. If I said, hey, evaluate this big function at negative 3, I'd have to take negative 3, plug it in here, 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 and then evaluate that using a calculator, or worse, if you didn't have a calculator. Or you could plug this function into y1 and then go to your table of values at negative 3 and look up the output. Those are all ways that you could do that. But we're going to show in the next video how you can do these evaluating functions just using synthetic division. So stay tuned and I'll pick up on the next video.